11 says what? A gas occupies a volume of 410 milliliters. All right. Then it says that that is at 27 degrees centigrade and 740 millimeters of mercury. So that's a pressure. So there's all of my initial conditions. Then it says calculate the volume, that's what we're looking for here at V2, if we are at STP. Okay. Well, the standard temperature is 273.15 Kelvin, and this is 760 millimeters of mercury. All right. So we're going to start out with P1 V1 over T1 equals P2 V2 over T2. Then we're going to rearrange that to P1 V1 T2 divided by P2 T1 equals V2. Okay. So P1 is 740. V1 is 410. T2 is 273.15, P2 is 760, and then T1 is 27 degrees centigrade. Can't use it. 300.15, Bobby, right? And then Bobby's got it going, right? Not David? 300.15. Where's my calculator? Here we go. All righty, 740 times 410 times 273.15. What'd you get? Wonderful. Did you get that? Let's take a look. See, milliliters, yes. Did we get that? No. No. I mean, you should, but I'm not that kind of guy in this kind of class. You know what I mean? Yes. Wonderful. All right. How are we doing? Number 19. A mixture contains 600 torr of hydrogen. It contains 200 torr of nitrogen and 300 torr of oxygen. What's the total pressure? Does anybody not get that?
I'd give a bunch of those.
Like 50% at least.
You have no idea how long it took me to calculate that.
All right. Took a long time, huh? Number 23. How many moles of oxygen will occupy 1.75 liters at STP? All right. So we're looking for moles. 1.75 liters is what's given. So we've got PV equals nRT. We're looking for moles. Which one of these is a mole? N. So N equals PV over RT. STP, standard pressure, 1. Volume, 1.75 liters. 0.0821 liters atmosphere, mole K. And temperature, 273.15, right? Because it says the standard temperature. Okay, 1.75 divided by 0.0821 divided by 273.15 equals, yep, I did that, 0.078 moles of O2. Wonderful, she's using units.
It says in the back of the book that one more than any gas occupies 22.12
That is only at STP. Okay. Now, only at STP, 1 mole of any gas occupies 22.4 liters. Okay. So let's take a look here. 1.75 liters. We are at STP here, right? 1.75 liters, so it's going to be 22.4 liters per 1 mole. So 1.75 divided by 22.4 is? Why don't I do that? Okay. 1.75 divided by 22.4? It's the same answer. Okay? Either way you want to do it, I really wanted to get away with not using this. Let me tell you why. Because this only works when? When does this work?
Always.
Oh, well, we don't want to say that. In this classroom, it works always, right? Because that's what's called an ideal equation. What is an ideal gas? Well, an ideal gas is a gas that is at a reasonable pressure. Now, what's a reasonable pressure? Atmosphere, inside of a tire, something like that's reasonable pressure, okay? Or even a little bit less than atmosphere. And it has to be at a reasonable temperature. What's a reasonable temperature? I don't know. Somewhere around where waters are going to boil and freeze and anywhere in between, okay? A gas will not behave ideally if it violates those conditions. So like if you want to talk about what's happening inside of a lightning bolt, this here ain't going to work for you. You have to use what's called the van der Waals equation. All right? If you want to talk about an extreme high pressure reaction, that ain't going to work for you either. Now, the second criteria is a gas must have elastic collisions. You know, what's the two types of collisions that you've got in physics? Elastic and inelastic, right? So an elastic collision, that would imply that when something hits, they just completely bounce off. Ping pong ball, that's an example of an elastic collision. Of course, it's not perfectly elastic, right? But it's an elastic collision. Then you've got an inelastic collision, like he chews a wad of chewing gum, I chew a wad of chewing gum. We throw it at each other, and they stick and go off into their own trajectory. Are you with me? So a gas can't do that and behave ideally. It must be totally bouncy. So in other words, the gas must be quote-unquote non-sticky. All right, let's derive it. This right here is the molar volume, so we're looking for the volume at STP of 1 mole of gas. PV equals nRT. Arranging the equation, V equals nRT all over P. Volume is going to be 1 mole, 0.0821 at 273.15 divided by 1. So what is this? Type it in your calculator. Oh, look at that magic number, 22.4 liters. All right. Are we good to go? Not good to go. All right. Getting one thumbs up from the back of the room. Okay. What are we doing next? Number 23, and the next was number 27. So have we got 100 so far on this test? Wonderful. 100 so far on the test. So if you can use your neighbor in a book, you're good to go? 10-4. All right, number 27. All right, number 27. Why don't you have a book? Ding dong.
Online class.
Well, can you not print it off?
Printer's down.
Really? All right, number 27. You're in an online class. Yeah, that's a trip. Okay, how many grams? So we're looking for grams of NH3 are in 725 milliliters. That is a what? A wonderful.